Welcome back to our number theory series.
Always great to be back.
In past episodes, we kind of explored like the basics of number systems, right? From simple counting and then to, I guess, more complex concepts like prime numbers,
Yeah.
divisibility.
Yeah.
Today, we're going to dive into a new area, the fascinating world of mathematical constants.
Yeah. These are really cool because they're deceptively simple, right?
Okay.
Numbers like pi or, the golden ratio.
Yeah.
But they underpin huge areas of math and even physics.
That's right. It's incredible how these fixed values, which are defined by very specific mathematical rules,
Right.
they can hold so much significance.
Yeah.
So in this deep dive, we're going to kind of go on a journey, a chronological journey.
Okay.
And we'll trace the discovery and the impact of some of the key constants in the history of mathematics.
Sounds good.
So where do we even begin with something like this?
Well, our journey, it actually begins way back in prehistory, long before we had written language even.
Oh, okay.
And even then, humans understood the concepts of 1, 2, and 1/2.
Really? So these very basic, like, counting numbers were understood that far back?
Yeah, they were essential, for early counting and measurement.
Right.
And it really demonstrates that, an innate human fascination with numbers.
Yeah, I think that's true. Like we've always been drawn to them.
Yeah.
For sure.
And these weren't just like abstract ideas back then.
Right.
They were really tools,
Yeah.
for understanding and interacting with the world.
That's fascinating. So from those very basic building blocks,
Right.
how did things progress?
Well, as we move forward in time, we start encountering constants like pi, tau,
Yeah.
both related to circles, obviously,
Right.
and then the square roots of 2 and 3.
Yeah.
Now, these emerge from geometric problems.
Okay.
Things like, trying to square the circle and understanding diagonals.
I see.
Think of figures like Pythagoras,
Of course.
whose theorem, is forever linked to the square root of 2.
Absolutely, yeah.
However, a lot of these constants were likely understood
Okay.
long before they were formally, given names or studied in depth.
That makes sense. It's like people were using these concepts,
Right.
but maybe didn't have the formal language or framework
Exactly.
to really define them yet.
Exactly.
So we have these early constants emerging from geometry. Was there any particular discovery that really kind of changed the game?
Yeah, I think the square root of 2 was a big one.
Oh, okay.
Because the realization that it could not be expressed as a simple fraction,
Okay, yeah.
led to this major discovery of irrational numbers,
Right.
which really expanded the boundaries of mathematical understanding at the time.
Yeah, so it wasn't just about the constant itself. It was about what it revealed,
Yeah.
about the nature of numbers.
Exactly.
That's really cool. So we've gone from 1, 2,
Right.
these very basic things, to pi, to the square root of 2.
Yeah.
What comes next in this journey?
Well, then we encounter the concept of zero,
Oh, 0. Yeah.
which might seem simple, but is actually pretty profound.
Yeah, it's interesting, right? Like it's nothing.
Right, but it's not just nothing.
Oh, really?
It actually represents what we call the additive identity,
Okay.
which is a crucial element in our number system.
I see. So it has a deeper meaning
Yeah.
than just the absence of something.
Absolutely, yeah.
Okay.
And then after 0, we see negative numbers emerging,
Right.
which further extended, the number line.
Yeah.
And opened up all sorts of possibilities.
That's right. It allowed us to represent things like debts,
Right, exactly.
directions, and just more sophisticated mathematical operations in general.
Exactly.
Yeah. So these early discoveries, it seems like they really laid the groundwork for some even more fascinating constants.
They did.
Yeah, these early discoveries, it seems like they really laid the groundwork for some even more fascinating constants.
They did, yeah.
I guess one that comes to mind is the golden ratio,
Oh, yeah.
often represented by the Greek letter phi.
Phi, yeah. The golden ratio has captivated mathematicians, artists, architects for centuries.
Really?
It appears, you find it in art,
Okay.
architecture, even nature.
Wow.
It's everywhere.
So what exactly is it? I mean, how is it defined?
So it's based on the Fibonacci sequence.
Okay.
Where each number is the sum of the two preceding ones.
Right. 1, 2, 3, 5, 8.
Exactly. So the ratio between these consecutive Fibonacci numbers, it approaches phi.
Okay.
Which is approximately 1.618.
I see.
But it's more than just, a mathematical curiosity. Like you'll find it in the arrangement of seeds in a sunflower, the spiral of a nautilus shell. There's this kind of underlying harmony in nature.
That's amazing. So we've gone from, ancient Greek geometry with these constants to, I guess, more modern constants.
Yeah.
What kind of bridges that gap?
Well, a key figure here is Leonhard Euler.
Oh, of course, Euler.
Yeah, one of the most prolific mathematicians
Absolutely.
of all time. And he's associated with several important constants, including Euler's number, which is represented by the letter E.
Right, E. So he might seem a little bit abstract, but it's actually crucial in calculus.
Yeah, absolutely.
For understanding growth and decay.
It's everywhere.
It pops up in a lot of natural phenomena, too.
It does, yeah. It might seem like a big jump from something like the square root of 2 to Euler's number, but it really demonstrates how mathematics builds upon those previous discoveries. It's constantly expanding.
Right, into these new realms.
Exactly.
It's pretty fascinating that Euler's number, like the square root of 2, is also irrational.
Right.
Its decimal representation just goes on forever.
Yeah.
Without repeating.
And yet it arises so naturally.
Yeah.
In so many different contexts.
They're like it's pointing to something.
Right.
Fundamental about how the universe works.
Exactly.
So Euler is also associated with another constant, right?
It is, yeah.
Euler's constant.
Also known as the Euler-Mascheroni constant.
Okay.
Represented by the Greek letter gamma.
Gamma? Okay. And what's the deal with that one?
Well, this constant, it's related to the harmonic series.
Okay.
And it's still somewhat mysterious, honestly.
Really?
Yeah, so we know its value to a high degree of precision, but we don't actually have a closed form expression for it.
Okay, so we can calculate it.
Yeah.
But we don't have a neat little formula.
Yeah, like a tidy formula.
To capture its essence.
Yeah, we haven't quite figured that out yet.
It's intriguing that even with centuries
yeah, I know, right?
of mathematical exploration,
yeah,
there are still these secrets out there.
There are.
Waiting to be unlocked.
Absolutely.
And the world of mathematical constants, it doesn't sound like it's static.
No.
It's always expanding.
It's constantly growing, yeah.
So how many mathematical constants are out there?
Well, there are hundreds that we know of.
Wow.
And each one has, its own story, its own role in various fields.
Okay.
For example, take the MRB constant.
MRB, okay.
Now, it's derived from a seemingly simple alternating series.
Okay.
But its value is both irrational.
Okay.
And more importantly, uncomputable.
Uncomputable? What does that even mean?
That means we can't define a finite algorithm to determine its exact value.
So we can't, write a program?
Right.
To spit out the number?
We can't calculate it exactly. We can approximate it.
Okay.
But we can never pin it down precisely. Huh. It really it challenges, our assumptions about what we can truly know for certain in mathematics.
So there's a whole category.
Yeah.
Of uncomputable numbers out there.
There is, yeah. And that's part of what makes exploring mathematical constants so alluring.
Yeah.
There's always something new to discover, another layer to peel back.
So what other, I guess, strange and wonderful constants are out there?
Well, consider the Champernowne constant.
Okay.
Now, it's constructed by stringing together all the natural numbers in decimal form.
Okay.
So you have 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Wow.
So on and so forth.
It seems a little arbitrary.
It does, yeah. Almost whimsical.
But it has deeper connections.
It does, yeah.
To other areas of math.
To other mathematical areas, yeah.
It's like a tapestry.
It is, yeah.
Woven from the fabric of our counting system.
That's a great way to put it, yeah. And it illustrates how even these seemingly random constructions can have a very rigorous mathematical definition.
That's pretty cool.
Yeah. And then, of course, you have constants related to prime numbers.
Oh, okay,
Like Mills' constant.
Mills constant. Okay.
Yeah.
What's special about Mills constant?
Well, it has this remarkable property. It generates prime numbers.
It generates prime numbers.
It does.
Yeah.
So if you raise Mills' constant to the power of 3,
Okay.
take the integer part of the result, you get a prime number.
Okay.
Raise it to the power of 3 squared, take the integer part, another prime number,
Ah.
and so on.
It's like a secret code
Yeah.
for unlocking the sequence
It is, yeah.
of prime numbers. Exactly.
We're uncovering hidden treasures
Right.
in this vast expanse of mathematics.
That's what it feels like, doesn't it?
It does.
Yeah. And like any treasure hunt, there are still mysteries to be solved.
Oh, okay.
Remember Brun's constant?
Brun's constant.
Which is related to twin primes.
Right. Those pairs of prime numbers that differ by only 2.
Exactly. Yeah, like 11 and 13.
Yeah. Twin primes always felt special.
They do, don't they?
Yeah.
Yeah, so Brun's constant is the sum of the reciprocals of all the twin primes.
Okay.
And we still don't know for sure if it converges to a finite value
Okay.
or diverges to infinity.
Oh, wow. So there's a fundamental question about twin primes.
Yeah.
Are there infinitely many of them?
Exactly.
You don't know.
We don't know for sure, and Brun's constant is really intertwined with that question.
I see.
So proving its convergence would strongly suggest there are infinitely many twin primes.
Okay.
If it diverges, well, the mystery deepens. Wow, so we've covered a lot of ground here.
We have.
From those simple constants like 1 and 2,
Right.
all the way to this uncomputable MRB constant.
Yeah, it's been quite a journey.
It has, but why should anyone care?
That's a good question.
You know, like why are these mathematical constants important?
Well, they might seem kind of abstract, right?
Yeah, they do.
But they're like a hidden code
Okay.
that makes our universe tick. They're not just living in some separate realm of pure mathematics, you know.
Right, right.
They really underpin so much of what we take for granted.
So how do they actually impact like our everyday lives?
Well, I mean, you find them everywhere.
Okay.
Physics, engineering, computer science.
Mm-hmm.
They're woven into the fabric of our technological world.
Okay.
I mean, mathematical constants are at work behind the scenes whenever you use your phone, drive your car,
Wow.
even listen to this deep dive.
So they're not just theoretical constructs.
Yep.
They have like real-world applications.
Real-world applications, absolutely.
Yeah.
They allow us to make predictions, model complex systems, build bridges, design airplanes.
That's very cool.
Understand how diseases spread. They're silent partners in so many of our modern advancements.
It's really amazing to think that something seemingly so simple as a constant can have such a profound impact.
It is, yeah. And the story of mathematical constants, it's not over.
Okay.
We're still discovering new ones, and we're unraveling the mysteries surrounding others. You
Sure.
know, like Brun's constant and its connection to those twin primes.
So even after centuries of exploration, mathematics is still a living, breathing field.
Absolutely, yeah. There's so much more to learn, to explore.
It's pretty exciting.
It is. And, you know, keep your eyes peeled for these constants as we continue this number theory journey.
Okay.
You'll start to see them everywhere, like hidden gems,
Okay.
just waiting to be discovered.
So it's a challenge then. It's like a treasure hunt
Yeah,
through the world of numbers.
it is, absolutely. And the more you understand these constants,
Mm-hmm.
the more you'll understand the fundamental forces that are shaping our universe.
That's a powerful thought.
It is.
Well, thank you so much for taking us on this incredible deep dive.
It's been my pleasure. It's been really fascinating.
It's been fun. And remember, you know, the next time you encounter a seemingly simple number, just take a closer look.
Okay.
It might just be a mathematical constant with a whole universe of secrets.
Yeah, waiting to be revealed.
Exactly.